Hi, this is Ikram Hussain Tai. I'll be presenting and explaining a research paper titled Catching Transparent Fish, Analyzing and Detecting Men in the Middle Phishing Toolkits. In this presentation, I will go through the paper section by section. I will explain what this research paper is about, what the key findings were, and what the solutions the researchers proposed to detect and prevent these MITM phishing attacks. So let's start by looking at the abstract of the paper. It gives us a quick overview of what this research is about, what problem it focuses on, and how the researchers approached it. This research explains how phishing toolkits have made it much easier for attackers to create fake websites and steal information. Recently, this new generation of these tools has appeared and it's called Man in the Middle Phishing Toolkits. Unlike older phishing pages that were just copies of a website, these advanced toolkits act as a malicious middleman between the victim and the real website. They show the victim a live version of the real site, but secretly record everything being sent, including usernames, passwords, session cookies, and even two-factor authentication codes. They examined how these toolkits behave on the network and identified certain network level patterns that can reveal when one of these toolkit is being used. And using these patterns, they built a machine learning model that can detect MITM phishing activity with 99% of accuracy. And their data collection system discovered 1220 active MITM phishing websites, but surprisingly, most of them were not listed on phishing block list, meaning normal security systems completely missed them. And finally, researchers proposed a new technique that online services could use to fingerprint and block suspicious traffic from these toolkits in real time that will help prevent users from being tricked in future. So this is the introduction to the research. In this section, we will see how phishing evolved over time. So we know that usernames and passwords are extremely valuable to attackers. Once they have them, they can access bank accounts, email, social media, anything. And one of the most common ways attackers get these credentials is by phishing, where they trick people into giving their information by pretending to be a trusted company or a person. In the early days, attackers would build fake websites. They will clones of a bank or email login pages and host them on their own servers. That required a lot of manual work, copying pages, keeping them updated so they still looked real, and collected credentials user typed. Then these phishing toolkits appeared. They automated much of that work grabbing like static copies of pages, serving them to victims, and using cloaking tricks so only intended targets saw the malicious site. This made phishing much easier and cheaper to run. So this is how it works. We can see it in this diagram. So to solve the limits of static pages, attackers move to a new approach. And this is what we can see here, man in the middle phishing toolkits. These act like a reverse proxy, basically a middleman server that sits between the victim and the real website. And because the proxy forwards live content from real site, the victim sees an identical up-to-date site. There is no need for attackers to clone or maintain pages. When the victim submits credentials or two-factor authentication codes, those pass through proxy and are captured by the attacker before being forwarded to the real site. The researchers examined 13 versions of popular toolkits and created a controlled dataset by deploying the toolkits across many locations. And this is how they observe how proxies affect network behavior from many geographic perspectives. They found that MITM toolkits introduce measurable differences at the network level, especially. For example, timing delays, differences in TLS caused by proxying. Using these features, they trained a machine learning classifier that can detect such toolkits with 99% of accuracy in their experiments. And that's very high. It means model is really good at telling proxy-based phishing servers apart from normal websites. And they packaged the detection into a tool called FOCA, which is used to probe fingerprint and discover MITM phishing instances. And using FOCA crawling certificate logs, blocklist feeds for a year, they discovered 1220 real MITM phishing websites targeting big services like Google, Yahoo, Twitter, and Facebook. And most of these sites were not on existing phishing block list. Only 44% of domains and 19% of IPs were listed, which is very serious. So now let's go to the section 3 of this research paper, and here we will see MITM phishing toolkit classifier. So to detect phishing servers that act as proxies, not the old static pages, but the servers that sit between user and real site and forward live traffic. Because attackers fully control page content, the researchers focus on network level fingerprints, signals like timing delays, TLS implementations, and those details which are obviously harder for attackers to change by editing HTML. And they study three real-world toolkits, and which are Evelgings, Morana, and Modlichka. Each of them have different capabilities. Using a lab and real-world measurements, they build a data set to train a machine learning model and wrap the results into a tool that we discussed previously, which is called POCA. So let's see what counts as MITM phishing toolkit. So to avoid confusion, the paper defines exactly what they mean by MITM phishing toolkit. It's a reverse proxy that mirrors real website to victims while forwarding requests to the actual server. And importantly, the proxy gets sensitive material in the transit. It includes usernames, passwords, two-factor authentication codes, and also session cookies. Because the proxy forwards traffic both before and after login, the victim sees a working session and keeps browsing, which makes the attack harder to notice. And they exclude phishing tools that only host static copies or don't forward live traffic because these have different network characteristics and would confuse the analysis. So the focus is mainly on the true proxy-based phishing toolkits in this research. So let's look at these three toolkits they mainly focused on in this research. So the first one, which is Evil Jinx, it includes a command line interface and can run DNS automatically and request real TLS certificates via Let's Encrypt and host many phishing pages as subdomains. It also uses tokenized URLs, random tokens appended to links, so only intended victims see the phishing page. That token system helps attackers hide campaigns and quickly disable tokens if they are discovered. And the next one is Modlishka. Is simpler and more manual. It typically targets one domain at a time and doesn't automatically request real certificates. It usually generates self-signed certs unless attacker supplies a real one. And Modlishka can also be set up to strip certain security headers, changing how request looks to a server. And the third one is Murana, and that automates more of the process. It crawls site to learn which bits of HTML to rewrite and pairs with a tool called Necrobrowser that can use stolen session cookies to automatically perform actions like changing account settings without manual intervention. So here we will understand why network timing matters. The core idea of detection is timing. So reverse proxy creates two logical links, one from the victim to proxy and another one from proxy to real server. The initial TCP handshake may be answered quickly by the proxy, but the actual content, the HTTP GET response, often takes longer because proxy must forward the request and then wait for the origin to reply. And these differences show up in RTT ratio. For example, the ratio of TCP SYN egg round trip to the HTTP GET round trip. If both come from same machine, the ratio is small. If the GET goes via another server, the ratio increases. And the researchers make both valid request and malformed one to reveal how the server responds. And that's where we can notice a huge difference. And that's what the researchers used to to train that machine learning model that we will see in this presentation. So this figure compares network response time between normal website and MITM Phishing Toolkit. So on each chart, the horizontal axis shows the ratio to round trip times, basically how much slower one type of network response is compared to another. And the black dashed line represents a normal direct connection to a legitimate web server. In short, this figure gives us experimental proof that MITM phishing servers behave significantly differently from a normal websites and that these differences can be used for automated detections. To train their machine learning model, they used two types of features. First, network timing features. There's, these features measure RTTS at several points in TCP, TLS, or HTTP exchange for both normal and malicious request. Timing is associated with network path and number of hops, so it's hard to fake without changing infrastructure. And secondly, TLS library features. Many of these proxy toolkits use specific TLS libraries such as Golang Stacks, TLS Prober, which produce distinct TLS fingerprints. So in total, model uses 199 features, about 14 timing features, and 185 TLS related features, which would make evasion difficult because an attacker would have to change many low-level behaviors. Let's look at dataset collection and lab setup. So to build a reliable model, they needed examples from many network setups. So crucially, they launched 30 globally distributed AWS nodes. Each node ran client, toolkit, and Apache target instances. By permuting which node acted as a victim, proxy, or origin, they generated many realistic geographic combinations. For example, reflecting how a victim in Asia could be proxied through Europe or US origin. This gave them huge coverage of real world timing variability. And this setup produced 73,080 measurements per toolkit and 146,160 data points overall, which is a strong data set for training the classifier. So this figure shows the worldwide setup the researchers used to collect network timing data. So each small icon on the map represents AWS node placed in different regions around the world. For example, North America, Europe, Asia, and Australia. And these nodes simulated three different roles: a victim, a phishing toolkit proxy, and a target web server. So the traffic was sent between them in different geographic combinations, shown here by colored lines. In short, this figure illustrates how the researchers collected thousands of timing measurements across many network paths to train their detection model. So for modeling, they used a random forest with 100 decision trees, and a minimum split of two random forests are reliable and give insight into feature importance, which is helpful for security applications. They trained on balanced dataset with equal phishing and benign samples and achieved 99.9% accuracy with five-fold cross-validation. And by the way, random forest is a machine learning method that builds a forest of many decision trees to make more accurate predictions. And to test whether the model relied on a small set of fragile features, they iteratively removed the most features and retrained. They also tested models using only network timing features or only TLS features, and both performed very well. This redundancy means attackers would have to change both timing behavior and TLS stacks to evade detection. Here we can see the researchers gradually removed the most important features one by one and retrained the model each time to see how its accuracy changed. On the chart, the black dots shows accuracy, and you can see it stays almost flat around 99% for a long time. Even after removing more than 100 features, the false positive and false negative lines stay close to zero as well. So this table shows how well the machine learning classifier performed under different testing conditions. In part A, model is trained using only one feature group at a time, either network timing or TLS features. In part B, the classifier is trained on the oldest versions of each toolkit and then tested on newer releases. The accuracy stays very high, around 98 to 99%. And in part C, they completely remove one toolkit's data from training to see if the classifier can detect a new unseen toolkit. And accuracy drops slightly, even less than 2%. So overall, this table shows that the classifier is accurate, stable, and generalizable even across different feature and groups, toolkit versions, and unseen toolkits. So now we are going to discuss section 4. We have seen how classifier and the tool Poca were developed and trained. So now let's see how the researchers used these tools in the real world to actually discover and analyze MITM phishing websites in the world. The researchers used FOCA tool to scan the internet for man-in-the-middle phishing toolkits, those advanced phishing systems that intercept real traffic between users and legitimate websites. So over the course of a year from March 2020 to March 2021, they monitored thousands of suspicious sites in real time. The goal wasn't to just to find individual cases, but to understand the entire ecosystem, how attackers deploy these toolkits, what brands they mimic, and where in the world they are hosted. So researchers designed an automated crawling setup that behaves like a real user visiting a page. It loads suspicious websites using Selenium, captures all technical details such as certificates, network delays, and then passes that data to Foca, which decides if the site is using a MITM toolkit. By pulling data from multiple open phishing feeds and certificate logs, this crawler can find both known and brand new phishing pages at the moment they go live. Here we see the architecture of framework used to collect network data on real-world MITM phishing websites. So on the left, we have the phishing URL sources, things like certificate transparency logs and phishing block list that provide suspicious URLs. In the middle, we have crawling module that handles data collection. The scheduler decides when the URLs are crawled, and the recrawl module revisits them later. And on the right, the analysis module uses this data for content-based clustering to group similar phishing sites and for website analysis to study their structure and behavior. Overall, this setup automates entire process from finding phishing URLs to crawling, storing, and analyzing them efficiently. So, data source and filtering. So, instead of scanning the whole web blindly, they watched certificate transparency logs, records of all HTTPS certificates ever issued. When a certificate looked similar to a well known brand, the crawler checked it automatically because the tool relies on how the server behaves at the network level, not on what the page looks like. It can identify hidden phishing servers even when attackers disguise or block their content from scanners. This approach is ethical and privacy safe. It allows large scale monitoring without viewing users' personal data. So let's look at experimental phases and results. So they ran this study in two phases. In phase one, they did a pilot run combining certificate transparency logs and public phishing block list, and captured 206 MITM sites, 17 from block list feeds and 189 from CT logs. In phase two, they optimized pipeline to rely only on certificate transparency logs, which scaled much better. They detected 6,875 candidates, 6,875 candidates, and 849 from Facebook's CT API and 6,026 from custom CT parser. And then they performed a manual human review on roughly 7,000 candidates and confirmed 1,220 true MITM phishing sites. And after verification, overall false positive rate was about 0.6%. And after they filtered out domain parking servers that behaved like proxies, the false positive rate dropped to 0.67%. In short, moving to certificate transparency only detection massively increased coverage, and careful filtering plus manual review kept false positive very low. So this figure shows monthly discoveries of MITM phishing sites. The steady upward trend shows these attackers are becoming more frequent. It's confirmed that MITM toolkits are on the rise. So this is geographic distribution and hosting patterns. This slide shows where MITM phishing servers are located and how attackers are hosting infrastructure strategically. They found that these servers are spread globally but are densely located in North America and Europe, mainly because these regions have a lot of major cloud hosting providers. In short, attackers exploit cloud convenience and reputation to make their phishing operations faster and harder to block. So this figure shows timing and lifespan patterns of MITM phishing websites. So figure A on the left, we can see number of phishing domains plotted against days before detection. The middle shows how quickly these sites go online after certificate issuance, and figure C shows that how long these phishing sites stay online. While most disappear within a few days, but some stays online for several weeks or even months. So here we can see which brands are most frequently targeted by MITM phishing attacks. On the right, we see popular brands like Instagram, Google, and Facebook on the top. And the bar chart on the left shows domain manipulation tactics attackers use. The most common ones are combo squatting, which means where attackers add extra words around the brand name. The next one is target embedding, which means inserting a brand name within longer domains, and typo squatting, which relies on small spelling errors. Overall, the data shows that campaigns heavily target high trust platforms like social media, email, and payment services. This table here shows the top level domains used by MIT phishing sites, and we see that .com domain clearly dominates since it looks authentic and trustworthy to users. And here are the key takeaways from section 4. So the researchers proved that POCA can detect MITM phishing toolkits in the wild with high accuracy. And these attackers are growing, often target major brands and remain hidden from block list for days. But the network level fingerprinting can expose them early. So here is section 5. So in previous sections, we saw how POCA detects phishing servers from user side. Now we see it from website side. The question is, can a website tell when it's being accessed through a phishing proxy? So the team had to look deeper into TLS handshake, the encrypted communication setup. So MITM toolkits use different TLS stacks than real browsers. So their handshake signature called JA3 fingerprint can expose them instantly. So here is TLS fingerprinting and results. To detect MITM phishing toolkits from the server side, researchers focused on TLS handshake. They built a test web page that automatically collected each visitor's HTTP headers, IP addresses, and JA3 TLS fingerprints. So overall, a web server can instantly recognize and block MITM phishing proxies just by analyzing their TLS handshake, and that's long before attack reaches and the user, I mean, the website the attack appears on block list. And this table shows diversity of TLS fingerprints collected from several devices and browsers. You can see there is a wide mix: Windows, Android, iOS, macOS, even Linux and PlayStation. And this is the discussion. So it summarizes the key points that we covered previously, like impact and urgency. Like MITM phishing toolkits create near the perfect fake sites that magnify user harm, and there is fingerprinting opportunity that we discussed earlier. Block list blind spot, practical mitigations and limitations, and the last one is lab derived data sets need continual updating, edge cases, and all. So, in conclusion, this research found out how modern MITM phishing toolkits have made phishing more dangerous by perfectly copying real sites. But the same proxying behavior creates measurable network and TLS fingerprints. So finally, finally they introduced server-side TLS fingerprinting, providing that even targeted websites can recognize and block phishing proxies based on their handshake patterns. And they They actually discovered more than 1,200 phishing sites targeting brands like Google, Facebook, and PayPal, most of which are completely missing from existing block list. Finally, all the datasets, code, and FOCA tool itself have been released publicly, enabling other researchers and security teams to use. So here is appendix. This is the code they use in Evelgings. This is how they configure. Here is the table list, all features used in phishing toolkit classifier. And here is the table that shows major brands and services that attackers try to impersonate in phishing domains. And here is the reference to this research paper. Okay, all right. Thank you so much for listening to this.